The theme of the story is the quest for an exact solution in general relativity. The starting point for such a solution is an idealized case, such as a perfectly spherical shape of matter, but the solution itself does not rely on simplifying assumptions. To find an exact solution, one must model states of ordinary matter or classical non-gravitational fields with tensor fields that obey relevant physical laws. These fields must give rise to specific contributions to the stress-energy tensor, which, when added up, yield a unique solution to the Einstein field equations. This solution is compatible with the amount and motion of any matter or non-gravitational fields and is illustrated by the symmetric second-rank tensor field known as the stress-energy tensor. The Einstein equation can be used to study the solutions of the Einstein equations with a fixed form of the stress-energy tensor, which can serve as a model for objects such as stars. The story highlights the importance of consistency in understanding the relationship between matter and the geometry of spacetime in general relativity. The theme of the story revolves around the challenges of finding exact solutions in general relativity and the trade-off between elegance and practicality. The energy conditions, which are crude tests used to restrict the eigenvalues and eigenvectors of a linear operator, are too permissive to be physically reasonable but also too restrictive to account for the Casimir effect. Einstein recognized the importance of a smooth Lorentzian manifold in defining an exact solution, but useful solutions can be found that are not smooth, such as those created by matching a perfect fluid interior to a vacuum exterior or impulsive plane waves. However, many exact solutions exhibit globally causally suspect features, such as closed time-like curves or structures with points of separation. Well-known exact solutions can be classified according to the intended physical interpretation of the stress-energy tensor, such as the absence of matter or non-gravitational fields, electromagnetic radiation, or a fluid. Models can also be organized using the Segre classification of algebraic symmetries of the Ricci tensor. Despite the challenges, the search for exact solutions continues, even for models of an elastic solid, where currently no solutions are known. The Newt-Kernewman-de Sitter solution and the Gödel-Dust solution contribute electromagnetic fields, positive vacuum energy, vacuum perturbations, and pressureless perfect fluids in the Einstein field equation. While solving these equations can be quite challenging due to their nonlinear partial differential nature, symmetry conditions have been established to simplify the process. By imposing conditions of symmetry under time translation or rotation about a symmetry axis, it is possible to reduce the equation to simpler systems. The use of frame fields rather than coordinate bases and algebraic symmetry conditions have also been effective in obtaining solutions. Even then, the equations can still be difficult to solve, but the symmetries of these equations can provide possible avenues of attack. The symmetries of the Ernst equation and the nonlinear Schrödinger equation are examples of non-trivial symmetry groups that can be exploited to find solutions. It is important to note, however, that while these symmetry groups are often infinite-dimensional, it is not always a useful feature. Finding explicit solutions to the Einstein field equation is a difficult task, leading researchers to seek qualitative properties that apply to all solutions, or at least to all vacuum solutions. The Belinsky-Zakharov transform allows for the transformation of one solution into another, similar to the Backlund transformations in Soliton equations. This transformation is related to Noether and Lie's notions of symmetry. Regrettably, even when applied to an understood solution, the outcome is sometimes poorly understood. Though a generic vacuum solution to the Einstein field equation can be specified by giving a few arbitrary functions, the question of global existence of solutions remains. Therefore, researchers focus on the local existence results and the global existence results that involve another idea. The stability of the Minkowski vacuum under small perturbations has been a subject of much research due to the highly nonlinear full field equation. The desired result that the Minkowski vacuum is nonlinearly stable was only proven in 1993 by Dimitrios Christodoulou and Sergiu Kleinerman, after introducing several innovative ideas. Similar results have been achieved for Landau-Vac perturbations of the de Sitter-Landau vacuum and electrovacuum perturbations of the Minkowski vacuum. However, under certain conditions, anti-de Sitter spacetime exhibits instability. Another concern is whether an isolated positive mass energy density concentration would yield a well-defined and non-negative net mass, Known as the positive energy theorem, the theorem was finally proven by Richard Schoen and Xingtun Yao in 1979, with an assumption about the stress-energy tensor's nature. Although the original proof was highly complex, Edward Witten presented a much shorter physicist's proof, which mathematicians have justified with challenging arguments. Variants of the positive energy theorem have also been supported by alternative arguments presented by Roger Penrose and others.